we are knowing that problems are there. So let us, and inertia will be reducing in the system. We have to adopt measures to improve the inertia also. And apart from that improvement, what right now is needed is that measure the inertia. Basically, we need to monitor the inertia because we have seen its crucial aspect in power system stability. So we have in Indian electricity grid code, which defines minimum inertia also. And it has a provision that in case there is, means if your minimum inertia, you should have that much of minimum inertia in the system so that whenever you have a credible contingency, the minimum nadir frequency post reference contingency should be above the first stage of your UFLS. It should not let the UFLS to operate. So that much of, means in terms of that, it allows that to maintain this minimum inertia, the system operator can bring quick generation, start synchronous generation on bar, and it also allows that you can go for the curtailment of wind solar power because it is going to impact the system stability directly. And now inertia studies are also a part of our CA transmission planning criteria. Request you that if you have any questions, put it in the chat box. At the end, we will take it up. So same is we have minimum inertia concept in the Indian system. Then NERC in the USA has a critical inertia concept, and Australian energy operators market and Australian electricity market operator, they have a minimum threshold level of inertia concept. So these are coming in all the places because of the high integration. These were not the earlier issues. Now it is coming into it. Earlier it were the issues of a smaller system, islanded system, which were more running on this kind of inverter-based resources. Now it has come to the entire system, means the larger power system also, because with the increase in the renewable penetration is there. So everyone is means all the grid codes also, you can see that there is a massive change in the grid code across the globe also. So inertia monitoring is important for operation as well as the planning also. Why for the planning? So for the planning, it is important, means with the evolution of the system, you need to check that how is the means the what kind of generation will be available during the future course of the time, what will be the demand pattern, what are the technology advancement. You have to understand the dynamics of the inertia during those period also, because for that you have to design your system and you have to take the action right now. So by analyzing the historical data and modeling future scenario, planners basically anticipate inertia related challenges, and they put appropriate measures into their grid expansion and planning activities, and they put some reinforcement measures also. And they will also see that requirement of what kind of technology that is required to resolve the inertia contribution, the problem of the fault level, the problem of reactive power issue, etc. In the form of like devices like synchronous, where to put some synchronous condenser, where to put a STATCOM devices like SVC and the fax devices like a STATCOM and SVCs. And then we have what kind of IBR technology you are going to use. Earlier, there was no grid forming, only grid following was there. So everybody was utilizing grid following. Issues are increasing. So, and there are, so that's why now the grid forming inverters has come. It is expected that they will help a lot to the system in the terms of what are the challenges that are being faced, black start services, reactive resources, faster controls, then in terms of inertia, frequency response, all these activities. And these kind of stability services are expected from the IBRs. And it also help in planning your defense mechanism for, for future power system when the inertia is low, how different controllers like the IBR technology is there, then the fax STATCOMs are there, how these are providing a response to the system in terms of active power for frequency control, in terms of reactive power for voltage control. And you have to check your defense mechanism you have to plan your defense mechanism in case there is a stability issues are there. So it provides basically a risk management for the system operators. It can check that in the future, whenever there is insufficient spinning reserve, I have certain amount of available fast acting spinning reserve into the system, how much battery energy storage is required to produce that kind of frequency support to the system in those period of time. And it also means the risk management, that you should not over rely on any specific generation technology. Otherwise there may be, because each technology has their own limitation, their own problem. So you have to do a balance between all those generation technologies. And you have to finer aspect is the last one is the with increasing IBR, the means and in large pockets, they are coming in large amount of complexes. The size of the complex of IBR are quite big, and they're coming in such means one particular pocket. So geographical distribution of inertia will now not be even, it will change. Now the scenario has come across the globe also. So that's where we are the concept of power system global inertia that has come to the regional inertia, depending upon where how much inertia is available in that but one particular areas. And in the operation, discussed that the inertia monitoring is very crucial for frequency stability. Means after post any contingency impact, you don't want to touch the under frequency load shedding. So how much response, fast frequency response, primary response, all this acting response should be there, and how much inertia should be available in the system so that after credible contingency, it should not touch the under frequency load shedding. All the other stability issues that we discussed, then rate of change of frequency based protection. In generally in India, we don't use for the generating plant, but across like Ireland and their other countries, they use a generator rate of change of frequency protection also. And they are testing that their generators are capable to handle 1 Hz per second rate of change of frequency because of the lower inertia in their system. And it also decide the inertia, the RE penetration level is how much to after how much RE penetration level we may face a problem of inertia in the system. So overall, this inertia monitoring will help in safe and secure operation of power system. These are some existing grid codes where this inertia, the changes has come in the recent years, and you can see that in many places, definition of inertia, minimum inertia level is there. In India, it is there. The calculation of minimum inertia methodology in India, it is still under development. As per the grid code is there, it is under development. Grid code was introduced in the October 2023. It has come into the force. So after that, lot of consultation are going on these activities. Then what kind of reserves are available, whether you have fast frequency response available from your inverter-based resources or not, whether they are mandated or not. Then what are the different other mitigating measures are there for the controlling the frequencies. So those with the reduction in the inertia. So these are there. So India is also on the par with whatever is the ongoing changes or the challenges that can be faced with the inertia. We already have introduced such actions in our grid in the form of our grid code also. So now we have we will discuss about the estimation methods. Quickly we will go through that. And the online inertia measurement. First we will have online inertia, then we will have some offline inertia methods also. So you can classify assessment of inertia in two basically broad categories basically. It is like we can have in the terms of usage, or you can have in terms of target level or time frame, data model, these kind of areas also. But if you look into the term how to estimate, different ways of estimating the inertia, assessment is like means how much is required, inertia is required in the system, and the second is how much is there, what is there in the system is the estimation method. So requirement, one thing is requirement for on the planning and operational part, that this should be available so that our grid is safe and secure. On the another side is that how much is available at right point of time or through the historical data, that you can utilize like offline method you can do, and online, and you can forecast the inertia also. And you can see the inertia at what is the requirement at system level. We were talking about regional level. You are talking about what should be the inertia of any particular generating plant or any embedded generation, what inertia contribution is coming from the demand and load. So you can have, means what I have observed is that lot of classification can be there. So in terms of estimation, there are basically two. One is what you do online and what is you do offline. Online can be model based also. Online can be complete. Online means what you are going to observe in the real time, what is the inertia in the system is there. Offline is basically you can compute through some real time data also, and you can compute it through some, kind of model also. So there can be a huge variation in the different means, classification is also there. So let us go through some of the aspect of inertia estimation. These slides it will be shared by the organizers, so you can later on go through that. So let us quickly go through the online inertia methods. So there are two aspects to it. One is kinetic energy, calculation of entire kinetic energy based on the unit commitment. So We will look into that how it can be done. And there is online inertia estimation using the VAMs and machine learning. The one side is a SCADA based information. You will use it for estimation of the inertia. Another side is more faster kind of, means data that is available from the synchro phasor data. So VAMs based estimation method. So what is kinetic energy estimation? So each of the system operator across the globe, they utilize the SCADA system basically. So what they get is that each of the generating plant, how much they are generating, where they are, whether they are in service or not, those information is known to them through their SCADA system. So what they can do is that they know that this particular unit is in service. Its inertia is already defined, the parameters are already defined when this particular machine is manufactured basically. At that point of time, how much inertia that is available with this particular generating plant, it is known. So it's a part of the generating unit parameters also, which is provided to the grid system operator. So you have one side inertia, and on the other side, it's current status, whether it is in service or not in service. And apart from that, the MVA. What is the capacity of capacity of this particular plant? So you already have this MVA and inertia, and whether it is in service or not. So what you can do is that compute this inertia by summation of its individual machine inertia multiplied by its MVA level. So MVA multiplied by some second, whatever that will provide you what is the kinetic energy stored in that particular machine. So what you can do is that after multiplying each of them, summate for the entire power system, what are the available machines are there. So what you can do, utilizing this, you can get that at this point of time, if this number of machines are in service, the entire power system kinetic energy synchronous, it will tell you about the synchronous kinetic energy available from all the generators into the system. Okay. So one thing is that for the right now. Another thing is that you also know that day after tomorrow or next day after tomorrow, what is your unit commitment strategy is there. So which unit will be in service and which unit will not be in service. So based on that, you can also forecast your kinetic energy also. And now based on those forecasts, throughout the period of the time, entire duration, you will see that whether and how the kinetic energy is varying throughout the day. And if you have, calculated by some simulation, some measures that minimum kinetic energy like this should be there, then if there is any breach in the unit commitment, if you see for the next day or next to next day, if any breach is there with this particular kinetic energy level, minimum kinetic energy, then you know that at this point of time, I need to introduce some additional generation into the system, or I need to change my unit commitment strategy so that I should not breach the minimum inertia level. So this is the way the real-time monitoring through the kinetic energy estimation is being done. So this is just a short summary. Limitations are there that it depends upon the, it excludes any demand side. Loads also have their own inertia. So it doesn't include those. And also basically, with accuracy it will always be dependent upon the SCADA data accuracy also. So because these are coming from remote signal and the remote field substation and coming through telemetry, if any issue in the SCADA data is there, if the details are not updating properly, then what will happen is that you may miss out. And you know that there are various embedded generation also. So these are not including the embedded generation within the, any particular industries are there. So it is just only providing whatever is connected, means, whatever is being monitored. Based on those monitoring the generators you are monitoring, we can utilize that for the estimation of the kinetic energy into the system. And this is the most widely and simple method to estimate the energy. Kinetic means measurement of inertia in the entire the practice, whatever is in the practice right now is there. So you can see that this is for India. So we have 5 regions. So each regions, how many units are there to net kinetic energy into the system, how it is varying throughout the day. So it is also showing that. Okay. So then if you go, you can see that there is a image in the morning, the load is picking up, but the solar is not there. So for that, more inertia is, more number of units are there. So inertia is more. While in the solar hour, some of the units are going down, shutdown can be there. So in those kind of days, where our inertia is less, in the evening peak hour is there. So we bring more number of hydro units into the service to meet this peak demand. So at that at that period of time, we have higher inertia, and based on that, and gradual reduction is there. So we will have this kind of. You let us say if I have set a minimum kinetic energy over there, so I know that if this is breaching this one, I need to put some additional generation resources over into the system or change my unit commitment strategy so that I should not breach the minimum inertia level. This means various countries examples are there. So you can see the Italy example. So when it is just means one side is the renewable energy, the green one is renewable, and the red one is basically the demand, and blue one is the inertia. So you can see that when low RE, they have a very high inertia. This renewable generation is less, inertia is more. High renewable energy, low inertia. So this is what they try to see, and they forecast the thing, and they see that on different days how the pattern is changing. So first thing is that you monitor this kind of thing. Start monitoring this kind of thing is very important to get a feel of the things that how the system is transition is the with the grid undergoing such a massive transition, how the inertia is getting impacted. Same is the ERCOT. What ERCOT has done is that the same thing, estimating, and they also forecast the inertia for the next 168 hours using the unit commitment plan. What ERCOT has means this is about the all the means everywhere the same kind of kinetic energy estimation method is used, and you can utilize your unit commitment plot to forecast the future inertia also, and based on that you can have means define your reserves requirement for the frequency control measures, for the frequency containment reserve, inertia requirement. Based on that, you can change your unit commitment philosophy to not breach the minimum inertia level. So this is the one of the way. Another way that is that has been utilized across the globe is that that one is the by G Vernova, and another is the EPRI they have developed is online inertia estimation method, and here we will look into the aspect of means regional inertia concept basically. So yeah, we have this various reference are there from where I have taken some of the crucial aspect of what we are going to discuss in the terms of how we can utilize the VAMs for the inertia estimation. So, okay, sorry, this one I need to, yeah. So in the power system, we know that inertia can be defined like this. Then if you have what is the stored inertial energy that is there, then we can utilize that for defining in the, means after you have df by dt, then pmt minus pet means electrical and mechanical energy, what is the difference is there. And using that, you can compute that for the next, means if you know the measurement of rate of change of frequency you are knowing, or if you are knowing the measurement of how much difference in the system or the change in the electrical power input is there, if these things are known to you through the measurement side, then what you can do is that you can easily calculate inertia, right? So basically what we have, the simplified equation can tell you that if you have the change in the energy in one particular area, how much energy change with the other system it is doing on the real time basis, and how much is the rate of change of frequency that you are observing within that particular system. If you have that, then you can estimate the regional inertia of that area. Like the combined inertia of the system, you can also estimate a local regional inertia. So let me just give you an example. I have, let us say, one particular A power system is there, which is connected to B power system through the two transmission lines. A has its own generation, this power system, and B has its own generation and load. So what we can see that I want to know the how much is the regional inertia contribution from power system A, and what is the regional inertia contribution power system B, and the combined inertia contribution. So combined inertia will be the summation of individual inertia of each area. So what I can do, I put PMUs on the lines which are getting connected from A to B. So whenever there is a disturbance in A, or when there is a normal disturbance in B, then there is a major change can be there. But let us say not talk about the larger disturbance. Let us say normal fluctuations are there. So if there is a normal fluctuation of load generation imbalance is going on, so let us say there is an imbalance in A area is there of 100 megawatts. So what will happen? Its own generation will try to slow down. Apart from that, it will also impact the whatever the changes in happening in that particular area, it will directly reflect on the basically on the tie lines of those, which is connecting area A to area B. So the delta P that changes between the area, that is the, let us say the power that was going from area A to B was 500 megawatt. Due to some event, this power is suddenly started to change from 500 to 510 megawatt with a certain rate of change of frequency. So rate of change of frequency is known from this. If you have a very good, means high accuracy device, having a high, reporting rate is at a very high rate, then what you can do is that you can easily estimate this kind of thing. And you can utilize this equation to estimate the original inertia, basically. Yeah. So this is the, the concept is like that entire power system, if we have the, if it's a large power system and which is very strongly coupled, then there is no requirement of regional inertia concept. Okay, so because let us say inertia is evenly distributed across the area, all the areas have their own generating plant and they are strongly connected to very good means the effective impedance between these areas and is less because they are connected with multiple transmission lines. So inertia is roughly more or less good, have a wide geographic distribution and a very uniform geographic distribution will be there. But let us say if this area has some generation is there and weak transmission line, 2 or 3 transmission line are there, and this is like, means it can be a longitudinal also. This is the case, means like the England or Scotland, all those areas are there. So there they have a concept there, you can utilize the concept of this regional inertia. Soon, if you have more amount of generation, let us say in India, Rajasthan pocket is there, large generation, renewable generation are there, and other conventional generation are, means it has to be shut down to, and for, means because initially generation from this power plant is quite high, and there are large power complexes, RE complexes. So there the inertia will be less compared to the entire system. So there we have again there also the concept of regional inertia will be there. So that's why means the inertia distribution depend upon the, means architecture, the design of the grid, the unit commitment philosophy, how we are going to operate the grid, requirement from the means, means the policy, requirement, regulatory requirement, and then the market requirements are there. Based on that, the entire things will change. The center means we have a means a good, well-connected power system. Now we are facing certain challenges in terms of IBR. So that's why the things are keep on changing. From global inertia, we will look into the concept of the regional inertia. So this is the basically this is the power system I was talking about. This has its own load and generation, and there is a tie line from this power system to the outer system. So this delta PB will be like whatever the change, let us say whatever the change in generation within this area, change in load in this area, and rate of change of frequency of the load and generation within this area. So this will be providing the equivalent center of inertia, means equivalent inertia, original inertia of this area. So let us say I'm talking about, I am talking about this area. So this generation is there, load is there, tie lines are there. So if I monitor this tie line variation through some PMUs, whatever I am observing is the change in the variation of this system, the load and generation response in this system, or the impact in what is going on within the system and how it is impacting the rate of change of frequency. If I have this tie line flow, rate of change of frequency within this area, I can utilize that tie line flow difference and rate of change of frequency to compute the inertia of this particular, let us say, A area. Similarly, I can do it for other areas also, and combined we will have a concept, means the entire power system inertia also, and as well as the regional inertia. And this will be very important key role it will play, because if we know that regional inertia is this much in real time, then there can be a requirement that we may face a requirement of minimum regional inertia level. In Australia, there are requirements that minimum regional inertia concept is there for each of the area, because it's also a longitudinal system and it has a, means distribution of inertia is, means it is not uniformly distributed across the entire Australian system. So similarly, we are going with high RE penetration. So we may face this kind of challenge in the near future, that we have regional inertia in one area very good, regional inertia in another area very less. So frequency variation will be more in that area, having less inertia compared to frequency variation in the other areas which are being given higher inertia into the system. So this is how because they keep on, they have the synchrophasor devices over there. They can do this to utilize for the measurements basically. So this is like this area, this particular power system, external area, put the PMUs and submit this PMU to get you the boundary of the power and weighted rate of change of frequency within this particular area, put multiple PMUs within the area and utilize the rate of change of weighted average of rate of change of frequency within this area. And then you will get the effective inertia of this particular power system. So this is how the synchrophasor based WAM or the WAMS based regional inertia monitoring or the inertia monitoring tools are being utilized across the utilities. So this is, means some summary on that letter you can give. So this provides you the regional inertia compared to the kinetic energy, provides the overall inertia in the system, how much is available. But here you get a feel of the regional inertia, how much rate of, if the rate of change of, if there is any tripping in one particular region having low regional inertia, then the frequency variation will be high. So there you need to have a more faster kind of response so that it should not breach the under frequency load shedding relay setting. And with higher inertia, you can have a, means lower response also. So it will decide what kind of fast response that is required in each of the particular areas, or what kind of means, rate of change of frequency based load shedding will be required in each of the pocket in the system. So this is, and apart from that, you can use the correlation between the existing, how much generation is there, how much load is there, and you have the effective inertia of the system is there, right? So based on the WAMS data in real time. So what you can do is that you can do a correlation analysis. If generation is going, renewable generation is increasing, what is the regional inertia level at that point of time? If the thermal generation is increasing, how these different generation are impacting this. So we can have and how the demand is also impacting it. So you can have a multiple correlation factor based on which what you can do is that if my generation of thermal is this much, hydro is this much, wind is this much, solar is this much, the correlation matrix will be there and you can predict the future inertia also. So that's how they predict the inertia forecast also using the WAMS that existing, whatever is data is there, and the unit commitment philosophy that you are going to adopt for the next day and the load forecast that you are going to have. So this is, they have done, the testings has been done. Some countries have deployed it like the Britain, which has a problem of lower inertia. So they have already deployed this kind of in their system also. So you can see the live inertia, they can predict the inertia in the real time also and check whether it is matching with the actual response or not. And there are ways to, this is on the side of the online, and there are ways in which you can do this offline inertia estimation also. And that's, means if you have multiple PMU data post, and these are post any kind of disturbances, then you can utilize this method. Sorry, here it is basically the heading is wrong. This is the method utilizing any large kind of disturbance and utilizing the PMU data. So what you can do is that if you have any disturbance over there, let us say one generation strip, you have multiple PMUs data across. Let us say in case of India, we have PMUs at all 400 kV, a station 765 kV. So I can collect those large number of PMU data, frequency data. I will remove the noises, and I will try to see what is the rate of change of frequency of means one frequency will be there which doesn't have more variation. It is not either accelerating or decelerating. It is somehow constant, means gradually falling. So that's basically the center of inertia frequency is there. And based on that, what we can do is that remove all the noises, notches, everything, and we have a filtering mechanism through which we can get a initial rate of this rate of change of frequency curve can be there. And you can estimate the initial rate of change of frequency by utilizing some curve fitting method. Okay. And if you have the initial rate of change of frequency, you already know how much generation has been lost into the system. And you also know that what is the MBA level in the system is there, how much generation is there, kinetic energy, you already know synchronous kinetic energy if you are monitoring that. So if you have prior to the just post disturbance, how much is the synchronous kinetic energy available from the SCADA, then you have this loss of generation is there. And from the PMU data, you already calculated the initial rate of change of frequency. You just utilize your power swing equation to find the how much inertia is available, what is the inertia at this point of time in our system. So this is the way you can utilize any kind of based on the PMU data distributed, means in a uniform way across the entire power system. You can utilize those data for computation of your inertia using a offline method also. It is basically the disturbance based method using the VAMPs. There are other ways also, like someone can put a perturbation into the system in form of like energy storage and ultra capacitor. This is one is being adopted by one of the companies, Reactive Technologies. So they have high speed measurement unit across various point in the grid, and they put, typically they put one modulator basically. So it can be a capacitor, ultra capacitor, it can be energy storage device. So what it does is that it put a, let us say grid based on the, depending upon the size of grid, it decides how much perturbation is required so that appreciable change in frequency is observed. So they capture the frequency and they know that how much delta P I have introduced into the system. So they capture the frequency in the entire system and they can calculate by utilizing the swing equation, they calculate the inertia. So they have probing signal, and based on that frequency, whatever the variation in frequency will be observed, and it will be decided by the inertia of the system. So this is also, it has been deployed in the various countries. They have deployed this kind of technologies, and the inertia based on the probing methods are also, perturbation method are also being utilized. So this is the overall architecture. You can go through there are papers also there, so you can go through that, and they have produced multiple places. They have shared their, means presentation also from where I have collected these details. So this is the overall crux of the inertia, importance, frequency control measures, then why it is important to monitor inertia, the impact it has on the entire power system with high IBR penetration, and what are the methods that are there and how it can be deployed also into the system.